Hi everyone, welcome to CHM 304 and 403 Electrochemistry Workshop Lecture 3, which is on polarography. After the lecture, I expect you to be able to determine the limiting current from polarographic data. I expect you to be able to determine the half-wave potential from polarographic data. I also expect you to be able to determine whether or not a process is reversible from polarographic data. There are two questions. The first one says the following potential E versus current measurements were made at 25 degrees C on a polarographic wave of the couple MZ/M. Here are the potential values measured against saturated calomel electrode. All the values are negative. Here is the current measured in milliamperes. All the values are positive. It says determine the limiting current, ILM, and the half-wave potential. This is the data. I went through the steps for actually choosing the right scale for plotting a graph in lecture 2, so I'm not going to go through that here. I'm simply going to show you the graph which I have plotted based on the scales I've chosen. 2 centimeters raised to 0.1 volt on the E-axis, which is the horizontal axis, and 2 centimeters raised to 0.5 milliamperes on the vertical axis, which is the I-axis. So the first point is 0.5 against negative 0.4. The next one is 1 against negative 0.41. The next one is 1.5 against negative 0.42. Next 2 against negative 0.42 again. Next one is 2.4 against negative 0.43. And then the last one is 3 against negative 0.45. Then I draw this curve, this S-shaped looking curve. Then I extrapolate from the base of the curve where the curve begins to rise, and then I do the same thing at the upper point. Then I draw a straight line across the point where the curve is more or less constant. I trace that point to the vertical axis, both upper and lower limit. I take the difference between these points to give the ILM, which is 2.85 milliamperes. To obtain E half, I divide the maximum current by 2 because it's half. I obtain 1.5. I trace to the point on the curve and then trace it back to the horizontal axis, and that gives me E half as negative 0.42 volts. This plot is known as a polarogram. Question 2 says the following potential E and current I measurements were made at 25 degrees C on a reversible polarographic wave for the process MZ being reduced to M. These are the potential values or negative measured against saturated calomel electrode. The current are in microamperes. It says if the diffusion current is 3.24 microamperes, determine the half-wave potential and the number of electrons transferred. Based on the Herofsky-Yukovic equation, which I have written, where E is the potential, E half is the half-wave potential, R is the gas constant, T is the temperature, Z number of electrons transferred, alpha transfer coefficient, which is 1 for a reversible process and less than 1 for a non-reversible process. F is Faraday's constant, I is the current, and ILM is the limiting current, which is 3.24 microamperes. Based on this, we draw the following data table. E, the potential current, we take the difference between the limiting current and the current and divide by the current. That gives these values. We take the natural logarithm of this to obtain this set of values. Next, we are supposed to make a plot of E against lane I, lane minus I all over I. We went through the steps for choosing the appropriate scale of plotting a graph, so I'm not going to go through that again. I'm just going to show you the graph which I have plotted based on the scale of 2 centimeters to 0.2 units on the lane I lane minus I all over current, and 2 centimeters to 0.01 volt on the E axis, that is the vertical axis, and this is the horizontal axis. On that basis, the first point, which is 0.415 against 0.19, which is this one. The next one is negative 0.422 against negative 0.43. That's the horizontal axis. Third point is negative 0.431 against negative 1.12. The final one is negative 0.445 against negative 2.28. Draw the straight line, and then we choose 2 points on the graph that intersect with the graph grid quite conveniently. For the lower limit, we've got negative 1.86 for the horizontal axis and negative 0.44 on the vertical axis. For the upper one, we've got negative 0.2 on the horizontal axis and negative 0.42 on the vertical axis. Based on this equation, which we've plotted this data, the Reversible equation, this is the intercept on the E-axis, which is this, and this is the gradient. So it says determine the half-wave potential and the number of electrons transferred. So the intercept on the E-axis, E half, is equal to negative 0.4175, which can approximate to negative 0.418. That is the E half. Next, from the Reversible equation, which is this, we know that this is the gradient, the slope. If we took these values which we got from the triangle, we say the slope is equal to the change in the vertical axis values against change in the horizontal axis values. This is what we actually have. This is equal to 0.0120 volts, and the whole of this is equal to this expression. So if we equate that expression to this, if we focus on these two bits, we can make Z, which is the number of electrons transferred, the subject of the formula, where R is the gas constant, T is the temperature. This is the gradient, alpha is the transfer coefficient, which is 1 for a reversible process, and F is the Faraday's constant. When we substitute these values, we obtain this expression. We obtain this value, 2.14, which is approximately 2. Therefore, the number of electrons transferred is 2. Thanks for watching. Links to the PDF version and study questions are below the video. That's the video description.